So, hello, we are Jimmy, Paul, and Gerald from ICS4A, and this is a video showcasing our lab implementation. So, I'm going to start you off with the first lab, which is socket programming, and I'll start off with explaining essentially what a socket is. So, what is a socket? Um, for there to be communication between two particular hosts, there needs to be uh, communication, and that communication needs to start with a particular endpoint, and that endpoint is a socket. So yeah, so whenever there's communication, for example, when in this case we are having communication between the server and the client, we'll have both the server and the client creating their sockets. So for example, in this code is the server code. You see that the server is the one who initializes their sockets, and their socket is a listening socket. They're listening to for a client to connect. So this socket is the essentially the local host IP address, and the port number for that particular socket is 5555, as you can see. So whenever a client connects, we can see that there is a message that is sent that they have connected. So on the client side, the client is the one who will first be asked if they want to connect to the server, they'll have to, okay, in this case, because we have already set the IP address and the port number exactly as the one that is being used by the server. You can see that they connect directly. So the same IP address and socket and the port number for the client. So for the as you can see back in the server code, the first line number 20, the buffered reader is used for reading the input, while the output stream is the one that is used to send messages to the client. While the input stream, as you can see from line number 29, is one that is used to receive that particular message from the client. So from socket programming can either be UDP or TCP oriented. TCP is for reliable communication, where you require communication to first of all be acknowledged, and it needs to be error free. So whenever there's an error, you can be able to reconstruct the messages. However, for UDP, the acknowledgement is not very necessary, and the errors can tolerate them, because at that time you require that communication to be very fast. So therefore, that acknowledgement is not required that much. So as you can see, uh, so I'll show you screenshots of how I did it. So first of all, I compiled the JavaScript, and then I ran the server first. When the server started, as I said earlier, they started with a listening socket. So that listening socket will be listening for a client to connect. Whenever that client is connected, the back and forth communication can now be done between the client and the server. And then now I'll move on to the second bit, uh, the second lab, remote method invocation. So remote method invocation is used for when is a whenever you want to connect to a remote server, you want to use the functions and the objects that a particular remote server has, uh, and make sure that it looks as if those particular objects and functions, they are already existing on the local computer. Use remote method invocation. So remote method invocation uses client, uh, the server skeletons and the client stubs. So let's start off with how it usually starts. So first, we'll compile all the JavaScripts. That is the client, the server, and the servant scripts. And we'll start with starting the RMI registry. The RMI registry is important because it's the one that is it's like the naming service. Yeah. So and then another important thing about remote method invocation, as you can see, this the objects and the functions, they have to be marshaled and unmarshaled, either between the local computer and the remote computer. Remote computer being the server and the local computer being the client. So these functions and objects are usually binded to the server, as you can see. So the servant is one which is acting in between the server and the client, is one which is doing the main program. For this particular program, for the remote weather invocation, it is like a calculator program where we see that the client, in this case, they'll be asked to enter string. Uh, they'll be required to enter a string. So this calculator program can also be like a concatenation program where you can concatenate two particular string. For example, this client, which was me, I entered my two names and they're able to be concatenated from the method that the function that was already on the remote function as the remote object, the remote server, sorry, which is this one, concatenation function, as you can see from here. So RMI is one which we use for that. Yeah. So as we can see, remote method invocation is also an extension of how it's like the way socket programming was working. Because the server is the one who initializes the communication, and then once they initialize the communication where they they have to set for example, in our program, we use the local host uh, IP address together with the same port 5555. So that the client can be able to connect to the same port, and that communication can be done. So whenever client is connected, they're able to invoke the particular functions and uh, objects that are in the remote server, as you can see. And then now we'll proceed to Corba. Corba is Common Object Request Broker Architecture, and it's it's used for it's platform independent. It's not like RMI. RMI is for Java. However, if you want to, for example, if the remote objects they are from either like C++, you can still be able to invoke those messages, those objects and methods using Corba. So Corba, the first thing that it uses this is the main uh, program. It initializes with the object request broker, or ORB in short, which is the universal translator. So uh, another thing that you can see, this program also has a calculator.idl. The IDL is the interface definition language. So Corba is used to translate this IDL into the stubs and skeletons as it was in remote method invocation. So the same way is being used here by Corba. So when that is done, Corba is able to translate these messages, these objects between these different languages that we are using. And the good thing about Corba, it's enterprise grade and has cross-platform communication, as I had said earlier. Yeah, so the same program is still being used here, but this one will now be a calculator program strictly. And I'll first take it to the README to see how we start it, because the code is pretty long. We'll start with the compiling the scripts. The scripts. Corba uses a lot of libraries, and that is what is being used here. And the rest are now the JavaScript we are using. Sorry. So we'll start with the naming service. The naming service is the ORB, as talked about earlier. And then this ORB is one which is one which is used for translating. And then we'll start now the server. The server, as it was in RMI and socket programming, the calculator server starts by listening using the same IP address and port numbers that we had seen earlier. And then the client is able to make uses the parameters they have in their local computer, and then invokes the functions that are in the remote server. Yeah. So when the calculator program will be essentially in the server. So whenever the client is making this calculation, the results will be gotten from the function that is already on the server, and then will be displayed the client, as you can see. Thank you.
This is Gerald Aduda, and I'm going to be talking about the two labs, the web services and the election algorithm. I'll be starting with the web services lab. So let me talk about web services first of all. Web services are like it's like a software system that is designed to support interoperable machine-to-machine interaction over like a network. It's usually done through like protocols like SOAP, HTTP, XMI, and it can either be done through SOAP or REST, but REST is more of like an architecture, and SOAP is like a protocol. It's just, so for web services, they're essentially like it allows two machines to communicate over a network basically. And in these web services, there are like four key things that you need to have. You need to have a service provider, a service requester, a service registry, and a service registry, and a service broker. The service provider is like the publishing service. It makes it available to potential requesters. So for example, for this lab of ours, we were trying to create a calculator service and making it available through the web. Our service provider in this case, since we are using Java code, is a Glassfish server. It was here in services under server. It's our Glassfish server. I can just start it. This is what allows you to connect to whatever web service you're trying to offer. Our service requester is the client app that will consume this particular service. And the service registry is the directory of, it's like a directory or like a list of the available services and it provides like metadata, more information like metadata about the services offered, like the endpoints, the WSDL, and a service broker is the mediator between the two. So in our calculator service, we had to, first of all, we are using Apache NetBeans, as you can see. You create the new project, choose that you want to run a Java web project, and you choose a Glassfish server. Make sure it's not too old, because I ran into an error where it wasn't working with JDK 21. So I had to revert it back to JDK 8 in the dependencies, but yeah, it works. After that, you come to web service, you create a new, and then it will be here web service. I'm not going to create one, but as you can see, this is what you get. Whatever I created will now come here, and this is my website calculator web service. It's basically a method that runs a method that takes two integers and adds them together over here. After that, we can just so after the service provider makes this available and it's running and you want to access it, our service requester in this case will be the browser we'll be using to access this service, because we are doing it through HTTP. If you're on another machine, like a remote machine, that will be our service requester because it's requesting this particular method. So I'll just run and I will test web service. Wait first. Let me clean and build. And then it's build success, and then I run it. Yeah, and then it's deployed now to the browser. For Apache NetBeans, it deploys to port 8080 automatically, but this is now the HTML file, the default HTML file, not the default. I obviously just did this, but if you want to get to the actual method, we can go to our calculator web service and then we test the web service. It gives us now like the details about it, like the WSDL or something like that. This is like when you're testing it in its raw form, and then this is when you're presenting it after. It's like building a front end for it. So we shall test it. Let's say you had to add number 23 and 67, right? Yeah, it gives you like more information about whatever this method is doing. The method parameters, the return, the value that has been returned, the SOAP request, which is the SOAP response. These are the most important things because it allows the client server and the requester server to essentially communicate with each other in this WSDL. WSDL is like a language that these servers use. It stands for Web Services Description Language. It's an XML-based language used to describe the interface of a web services, basically describing whatever has been exposed, whatever parameters are required for each method, and the format that is needed between the provider and the requester. So after that, we went further. We decided to see if we can port that method into HTML code, and we created a simple HTML form here, and we ended up using a SOAP request to call the method so that you can present it on a HTML file. And just to see if it works. Yeah, and then it brings back the result. This is basically how web services work. It's how most of the modern internet works, because many different systems, any two different systems, they need to talk to each other over the internet, especially if they're like written in different languages, like a Java backend talking to a JavaScript frontend, or maybe your iPhone app talking to a Python server. They need to use a web service. A practical example is like payment processing. Let's say you're buying something on Amazon and you need to make a payment. A web service will be requested between the Amazon website and your bank account. And the website packages your payment information, like your bank card, and sends it to Stripe's web service, or like PayPal's web service, or Visa web service, basically. And then the web service again will reply back with either payment approved or payment declined. Yeah, that's basically web service. And talking about the election algorithms lab, and I will start with the ring the ring algorithm, right? So um, for the core logic, basically how ring works, it's that the messages are passed around in a ring, which is basically the array wrapping from the last index back to index 0. The way this lab is set up, it's that you pick which process index initiates the election, and we'll call this is called the init, right? This is called init, and then from there, here this is called init, and then from there, init plus 1, the code walks around the ring wrapping to 0 when it hits the number. Num in this case refers to the number of processes that are in this system. For each process, if it's active and hasn't been already visited this round, it sends a message printed as process X send message to Y, and then its ID is appended to the array. And then the F flag, because the F flag is set so that it's it it's set so that it isn't messaged in the same pass. The F flag in this case, it's in this class, we were given they are defined. Each process is given an index, an ID, and a flag F. It is set as an integer. It basically helps us not go through it again. And then it also has a state. Each process has a state to indicate whether it's active or inactive, right? So this process continues until the ring comes back full circle to init. Once this loop is complete and it's finished, the code scans now the array for the maximum ID, and that becomes the new coordinator. The process is marked, that process that has become the new coordinator is marked inactive, meaning it is no longer a candidate for re-election, and is used as a marker for this is the current leader, rather than literally being inactive or down. So I'm going to run the code to so enter the number so here I'll enter the number of processes, right? Let's say I have 5 processes. Enter the ID of process. To be clear, let me just give them 1, 2, 3, 4, 5, so that you can see clearly what's happening instead of starting from 0. So 1, 2, 3, 4, 5. Right. So as you can see, we have 5 processes, right? Process one is mapped onto the index as position 0, process 2, 1, 3, 2, that way, so on and so forth. And then process 5 is selected as the coordinator. Let's hold an election. Enter the process number that initialized the election. For this, let's use like 3, right? So from 3, because we've put 3, it's now going to put an election from 4. It's not the process is going to start from process 4, then it goes to process 5, and then it will wrap back around to process 1. So from here, like you can see, the first thing it says is process 4 sends message to 1, process 1 sends message to 2, process 2 sends message to 3, process 3 sends message to 4, and then process 4 is selected as the coordinator. That's basically how the ring algorithm works. And then we can terminate that. Now I'll explain the Bully algorithm. So let me go to, yeah, this is the Bully algorithm. It's also a method of like choosing a leader, right? An algorithm that helps us choose a leader. For in this case setup, there's a state with a Boolean array of 5, and by default in this code that you gave us, it's all of them are default up, and process 5, which is the highest, works as the coordinator, which is basically how the Boolean will work. The highest number process, the highest number live process is always the leader no matter what. So even if like 5 is down and the highest is 4, 4 will always be the leader. If 4 is down and 5 is down and 3 is the highest, then 3 will always be the leader. That's why it's called bully, because the processes with lower IDs never get to be leaders, no matter what happens. So and in this code of ours, we have two main methods. There's this public static void up. This it's basically a method to bring the process back online. If it's already up and you run it, it stays up. Otherwise, it sets this particular process to active and it simulates an election. This is because it wants to find out who's the leader right now and or whether I be the leader, basically. It prints election messages sent to every process with a higher number. So if it's like 3, because of the way Bully algorithm works, it will search for higher processes and send only them a message, not the lower one. So it will send to either 4 or 5. Then it looks for the first live process to respond as alive. So even if 4 and 5 are alive at the same time, 4 will be the first to respond back to 3 that, oh, I'm alive. At that point, 3 terminates. It leaves the election up to 4. 4 in this case again will go up because it's still in the election process. If 5 is there, it will be like it will send a message to 5. 5 replies, I'm here, I'm alive, and then it seizes that again, and then 5 becomes the new leader. If 5 doesn't have anything, it sends a message to now to all of them and is like, I'm the highest one and I'm taking over the election and nothing's happening, basically. In here, this method, public static void down, it's basically taking a process offline. It simply flips the state of the process to false if it was up. If the sender's process is down, it just reports that, oh, there's nothing to take down because it's already down, which is basically this. If yes, it prints. If yes, it prints okay, and then business as usual, nothing happens. If no, the sender must run an election. It sends election messages to all the other processes saying, oh, I'm the new leader. If 5 is again higher than whatever it is, like if it's 2, it will send it to 3, and then 3 send it to 4, blah blah. And that process broadcasts the coordinator message to everyone becoming the new leader. So I'm just going to run a practical of whatever I was talking about. Public So in this specific code of ours, we have 5 active processes, which is whatever you give us. The processes that are up are P1, P2, P3, P4, P5. And since process 5 is the highest, process 5 is now named as the coordinator. Since all of them are up, I'm going to demonstrate down a message, right? Let's say I'm going to down a process. Let's say I down process, let me down process 5. So it's 5 that I'm bringing down. So as of right now, I've already set 5 to false. So sorry. So in this case now, 4 should theoretically be the new leader. And to test that, we're going to send a message. We can send it from P1, right? Process 1. Which process will send the message? 1. So this is the output we get. Process 1 is coordinating an election. Election send from process 1 to process 2. Process 1 to process 3, process 1 to process 4, process 1 to process 5. Coordinator message, it gets to process 4 and it realizes, oh, 4 is now the highest. And now coordinator, 4 becomes the coordinator, and since it's the new leader, since 5 has been removed, it sends a message to all the other processes saying, oh, I'm the new leader of this. And basically that's how it happens. Let's say I can up a process again. Let me up 5 and see what happens. We send a message from 4. Which person? Okay, it basically says that. Yeah, those are the algorithms.
Okay, so next I'm going to show how we did the the task on message passing interface. We implemented a simple program where we have non-root processes and a root process. And the non-root processes try to send a message to the root process, and then it is received, and then the message is displayed. Okay, so the non-root processes will send and assign a message tag, which helps the sender and the receiver match the communication, making sure that whatever is being uh, transferred from the non-root process is accessed and displayed in the root process. Okay, so the main logic here in this code is checking whether so for the current process, it's supposed to be 0, and this acts as the root process. So from 0, it starts looping through the remaining processes, which receive one message, and then the message is printed to the senders, which is ranked together with the received message. So this one, as I'm going to show how we did it, for when we run 4 processes, here when we run 4 processes, you can see the first one was checked for 0, and the next ones uh, are confirmed to have received the message that was sent from the root process. Here we did a demonstration of 10 processes. The first one, so the first one in the loop was used as a root process and was tagged at 0. And then the other remaining were used um, to send the message. Okay, so that's it on MPI. Okay, so the next one is Berkeley clock synchronization. So here we are trying to synchronize the clocks of different distributed machines. One acts as a master server, and then the others will acts as a client server. And for after every few seconds, the client sends their current clock time to the server, and then the server will try and compute the average clock difference of the client servers. So we did this using Python sockets for communication. So displayed here is the server code. Okay, so here we are starting with this function which tries to they start receiving clock time, which continuously receives the current time of each client and calculates the differences. Here it calculates the difference between the client's clock and the server clock. So here the master server will try and listen for new client connections. We're going to have multiple. Okay, so for this client file, we're going to open it on different tabs, and those will act as different like several clients acting upon this, interacting with this server, the master server. So here after every client is assigned their thread, so that those different the different clients that we have can communicate with the master server. simultaneously. Here we are getting the average clock difference, where synchronized synchronized time is done using the average clock difference, and then that is sent to the updated time back to every connected client. Okay, so that's just it. And then here in the client server file, so after connection is made to the server, we have two threads. One will periodically send the client current clock to the server, and the other one will wait for the synchronized time and will display that time after each cycle. So when we run, so this is the client, and sorry, this is the master server. We had 4 client servers. We opened 4 tabs and ran the client file 4 times. The client servers that we had. Here you can see the server collecting all the clock values and calculating the average difference. No, is it here? Sorry, when we run the client server, time was being sent in every loop after every seconds. So here you can see. So you can see the cycle. So here we were just trying to show how multiple server could be synchronized through a single master server. Okay, so next one. Mutual exclusion using token ring algorithm. So here we are ensuring that we're making sure that one process can access the critical section at a time by circulating a token between the participating nodes. So here we are having a server and client situation. So this is the server file. So here the server will continuously wait for incoming messages from the clients, and will extract the content of the information that's in the clients and display them on the console. So that's just the function of the server file. The first one here we have client 1. So this file begins with a token. The program checks whether it currently holds the token before allowing access to the critical section. Okay, so this is where data is being transferred from the client to the the main server. Here, a user can be able to send a data from the client to the server, and then I'm going to show how that's how we observed it. So here, when the user chooses yes, they have an option of choosing yes or no. When they choose yes, the client enters into a critical condition, and data starts, and then data starts being sent from the client to the server. When they choose no, then the client is expected to pass the token to a next node in the ring, to a next client in the ring. Okay, so the purpose of this file, the second client file, here the second client will start without the token. So we have the first client where they can start with the token. They can decide to start with the token and choose when they choose yes. But then the second file, it starts without the token, and it remains in receiving mode until the token is forwarded to it. So it will wait for the first client. And then when they receive the token, it will enter again it will now enter the critical section, and then the ring will continue, the loop will continue. So here we compiled the three files, starting with the client server. And entered a message on it. So the main server. Sorry. So here, yeah, I start. We run the first server, the main server, but then when we go to the client server one, this is where we can enter the critical condition. So we can be able to enter a message. I entered hello world just for trial to the server, and the server successfully received and displayed the message confirming that the first stage worked correctly. I also tried writing no, and the server entered into an error, and it never reached client 2, which remained waiting in the receiving mode. Let me show. Still waiting. But because client 1 already entered into a critical condition and was able to send the data to the main server, we can see it here. Thank you.